Welcome to the Air Distribution Design for Laboratories webinar featuring Titus Product Manager Matt McLaurin. Before we begin the presentation, please be aware of the following items. There will be a question and answer session at the end of the webinar. You're welcome to submit your questions at any point. The webinar will be available in the Titus University section of the Titus website and on our YouTube channel the following week or 7 to 10 days after the initial broadcast. For our Lunch and Learn attendees, to ensure everyone receives their CE certificate, please email us at communications@titus-hvac.com. CE certificates will be sent out after the completion of all 4 webinar sessions. Be sure to set your audio setting to mic and speakers instead of the telephone option. This will ensure there are no issues with hearing the session. Now let's begin the webinar.
Hello, and thank you to everyone who has joined us for our webinar today on air distribution designs for laboratory systems. My name is Matthew McLaurin. I am a product manager here at Titus for our critical environment diffusers and chilled beams, both of which are able to be used in the creation of high-performing laboratory air distribution systems. We'll get to examples of both types of systems at the end of the webinar, but we'll start out first with what labs are and how HVAC systems support their goals and objectives. From there, we'll move on to ventilation requirements that are out there. We'll follow this up with a closer look at fume hoods, their use, and how air distribution can affect their performance. Lastly, we'll cover the different lab classifications resulting from these ventilation requirements. We'll work through 3 examples of air distribution designs to meet the needs of a set lab space as the requirements for the ventilation change. A laboratory can generally be defined as a place providing opportunity for experimentation, observation, or practice in the field of study. As it relates to HVAC system design, we're mainly concerned with chemical, biological, and animal research labs. Other common labs that require specific attention from HVAC engineers and designers are physical labs such as physics, electrical, and microelectronics labs. From an HVAC perspective, we're looking to do 4 main things. 1, control exposure to any contaminants that are being used or created in the space. 2, contain any odors that are present or generated as a result of the experiments or testing. 3, provide adequate ventilation for the scientists or technicians present. And lastly, to provide cooling and heating to the space in order to maintain a more comfortable working environment for the laboratory staff. In order to control contaminants, a similar setup to sterile compounding pharmacies and clean rooms is used with a primary and secondary engineering control system. Within lab spaces, this is achieved by utilizing fume hoods as a primary engineering control mechanism. We'll discuss these in more detail later, but these devices are engineered to capture and retain any chemical or biological contaminants as a result of the experimentation or testing being conducted. The entire room then becomes the secondary engineering control, where we are preventing any contaminants and or odors from escaping the lab. This is achieved through the use of dilution ventilation, purging any contaminants that may have escaped containment within the hood, and by maintaining a negative pressure relationship to the adjoining spaces. In order to maintain a negative pressure relationship within the laboratory space, we need to supply less airflow to the lab than exhausted from the room. The volume of exhaust is based on the combined exhaust flow rates for the fume hoods utilized and the minimum required air changes per hour. The volume of this offset will depend on how tightly the room is constructed and the desired differential pressure. This offset is most commonly identified as a set airflow rate, typically between 150 and 250 CFM. Alternatively, a proportional offset control can be implemented where the differential is a percentage of the total exhaust airflow. There are some exceptions to this where the pressure relationship will need to be positive in order to prevent contaminants from outside the room affecting the experimentation that is to be conducted. These spaces are typically microelectronic or medical laboratories where the air cleanliness is critical to ensure the accurate results of the testing or medicines being developed. I've been referring to the air being removed from the space as exhaust and not return, and this is for very good reason. As we have discussed, one of the purposes of air distribution is to control exposure to contaminants as well as containing odors. In both cases, return of this air to the air handler would defeat the purpose of having these control mechanisms in place. As a result, almost all lab spaces will require 100% outside air for the primary system. Providing 100% outside air can be extremely costly. First, the air must be dehumidified to maintain space humidity, and then supplied to the space at the correct temperature. Depending on the conditions of the space, this might also include zone reheat to prevent overcooling. As a result, laboratories where the amount of makeup air is driving the ventilation requirements, the amount of this air required to ventilate and condition the space can lead to extreme levels of energy consumption. Determining the airflow rates for laboratories begins with looking at the thermal loads in the space. At a minimum, we need to supply enough air to maintain space temperature and humidity within the desired range. Independent of thermal comfort requirements, the minimum air change rate needs to be established next. There are lots of different references that address unique requirements for lab spaces. The most widely used of these is ANSI standard Z9.5. It is a laboratory ventilation standard established by the American Industrial Hygiene Association, and it recognizes that ventilation is a tool that can be used to control exposure to contaminants, but it should not be solely relied upon as a means of control and removal of contaminants, as it is generally ineffective. Instead, contaminants should be controlled at the source of generation, for example, within a fume hood. ASHRAE Standard 170, which covers laboratories and healthcare spaces, sets minimum requirements for the total air changes per hour, as well as the volume of outdoor air to be supplied and room pressurization requirements. However, it recognizes that a set ventilation rate will not meet the needs of all conditions that may occur and defers to ANSI Z9.5 as long as a hazard assessment and laboratory ventilation management plan have been established. The final component establishing laboratory airflow rates is the volume of air used by the fume hoods. These hoods are designed to capture and remove contaminants at the source instead of relying on the general room ventilation. The volume of airflow required by these hoods will depend on the type of hood and quantity used. In labs with negative pressurization requirements, ventilation rate is based on the exhaust airflow, which is used to minimize the buildup of odor and contaminants not captured at the source. In labs with positive pressurization, supply airflow establishes the ventilation rate as it is used to dilute the lab with clean air to achieve the desired level of air cleanliness. The primary source of contaminant control in labs are fume hoods. These are devices that are specifically designed to provide protection to the lab staff and occupant from the fumes, vapors, and particles generated by the operations being performed within the lab. Fume hoods keep contaminants contained using air that is being pulled through the face of the hood. There are a variety of different hood designs and manufacturers, but a common criteria established to contain the contaminants is capture velocity. This is the average velocity across the main opening of the hood and is intended to remain constant even as the sash position is adjusted. Maintaining this velocity is crucial to maintain effective contaminant control. While capture velocities can vary from manufacturer to manufacturer and between types of hoods, common capture velocities are typically around 100 feet per minute, but could vary between 80 and 120. There are also high-performance hoods that can have capture velocities as low as 50 to 60 feet per minute and remain effective at meeting minimum containment requirements even at these lower velocities. This can result in some air distribution design challenges that we'll address later. Capture velocity may also vary depending on local code requirements, OSHA requirements, or the unique requirements of the facility or organization that is operating the lab. And here, I'm waiting on Gary to do a rendering for me. Depending on how that turns out, we'll drop that slide in, or just extend the previous slide and have that run through all of what I'm about to say before I advance to the next one.
Okay, so just let me know when you're done saying what you're supposed to say about the rendering.
Yeah.
Okay.
Yeah. There are two main types of fume hoods: constant volume hoods, also known as bypass hoods, since they maintain capture velocity with bypasses as the sash position changes. Then there are variable volume hoods, that maintain their capture velocity by varying the exhaust airflow with sash position. So that part right there is what we'll have.
Okay.
With either type of hood, it is crucial to maintain the velocity across the face of the hood, which ensures proper operation and capture of contaminants. This velocity can be affected by external air motion, either from the movement of occupants and operators or from the air distribution. This can result in contaminants escaping the hood. The velocity of airflow in front of the hood should never exceed the capture velocity and generally should be about 50 feet per minute or less. It is recommended that velocities in front of the hood are designed to be within 25 to 50% of the capture velocity. With high performance hoods that have capture velocities around 50 feet per minute, this means keeping any air motion in front of the hood to a maximum of 25 feet per minute, which can be extremely challenging to maintain even without active air distribution. Now we'll move on to the types of diffusers that should be selected when designing a laboratory system. Typical ceiling diffusers with extended and high velocity throw patterns are intended for creating a well-mixed space, which could result in air streams traveling down the face of the hood or colliding with one another and causing drafts in front of the hood, preventing successful operation and should not be used. The best type of diffuser for this application is a radial throw diffuser. This type of diffuser has the ability to supply large volumes of air to the space with very short throw patterns. They're able to achieve this by inducing significant amounts of room air into their throw pattern and reducing the overall velocity in a very short distance. These diffusers primarily operate in zone 4 of jet expansion. This means that as airflow travels away from the face of the diffuser, they very rapidly slow down. You can see it has the highest slope of any of the types of zones of expansion. So as these diffusers induce a high volume of airflow, it adds mass to their flow, reducing their velocity very, very quickly. Radial diffusers should always be located such that the throw pattern is parallel to the face of the fume hood as shown here. Even when using one-way throw pattern radial diffusers, this rule should be strictly adhered to. With a one-way throw diffuser, even with airflow directed away from the hood, the induced air motion can pass in front of the hood, resulting in velocities exceeding even 40 or 50 feet per minute, disturbing the capture velocity. Radial diffusers are also unique in the fact that airflow travels in the direction of throw with little to no spread parallel to their flow path. This allows them to be placed relatively close to one another and to the fume hoods themselves. However, they should be placed at least 2 to 3 feet away from the face of the hood. There are 2 different standards that provide a means to determine that fume hoods are performing as intended when installed and operating within laboratories. Section 6 of ANSI Z9.5 covers commissioning and routine performance testing, and it's very similar to ASHRAE Standard 110. Both of these methods include airflow velocity testing, airflow visualization testing, and tracer gas containment testing, ensuring proper operation of the fume hoods within the air distribution system designed. Now that we have covered how laboratory ventilation is established, we can cover the 2 main categories of labs based on the HVAC system design. There are chemical and biological labs that typically have high exhaust rates because of the number of fume hoods used to contain the chemicals and biological agents. There are also animal laboratories and holding rooms which have high ventilation rates to contain odor and meet code requirements. In these spaces, the air distribution design is heavily driven by the exhaust rates, which exceed the requirements for conditioning the space. The other types of labs that we see are load-driven labs, where the airflow rates required to maintain space temperature far exceed that of exhaust requirements. These are typically laboratories resulted to physics and electronics where there are high sensible loads resulting from the equipment being utilized within the space. Due to the sensitive nature of the equipment used in these spaces, these are also typically under positive pressurization. Now we'll take a look at a few examples. For these examples, we will consider a 25-foot by 15-foot lab with a 10-foot ceiling. In these examples, the minimum ventilation rate will be 8 air changes per hour, which is 500 CFM based on the room volume. In order to maintain negative pressurization in this space, we will maintain a supply airflow rate of 250 CFM less than the exhaust flow rate. Sensible load in these labs is 17,280 BTU per hour. The fume hoods used in these labs will be 6-foot hoods with maximum exhaust flow rates of 650 CFM each and minimum airflow rates of 215 CFM. Capture velocity of this hood is 100 feet per minute. The first example we'll look at has 6-foot fume hoods. Using the design conditions we covered, we'll start by calculating our required airflow rates and then select and lay out diffusers for the space. Maximum exhaust flow rate for all hoods combined is 3,900 CFM and a minimum flow rate of 1,290. In this case, the minimum exhaust from the hoods exceeds the minimum air change requirements of 500 CFM, so no additional exhaust is required. In order to maintain negative pressurization in the space, we'll maintain the supply offset of 250 CFM. In practice, the amount of offset required to achieve pressurization will depend on how tightly the room was constructed and associated leakage. There will be a need to adjust this differential during balancing to achieve the desired level of pressurization. The result is 3,650 CFM for supply as a maximum flow rate, 1,040 CFM as a minimum supply airflow rate. In order to maintain space temperature at the maximum flow condition, a temperature differential of just under 5 degrees is needed. With this, we'll determine how many diffusers we need to use by looking at the performance tables for a domed radial diffuser. The first thing is to determine a selection that will keep velocities in the occupied space and in front of the hood below 50 feet per minute. This is half of the capture velocity for these hoods. As discussed earlier, if there is air motion in the vicinity of the open sashes excess of the capture velocity, we have a potential that the hood will not be able to contain the contaminants within the hood and exhaust them from the space. With the 10-foot ceiling heights, throws to 50 feet per minute must be 4 feet or less. While there are a couple selections for more than 600 CFM that will meet this criteria, the horizontal spread for those flow rates are too great given the layout of the room. Splitting this into 6 diffusers results in just over 600 CFM per diffuser. The horizontal spread at these operating conditions is 6 feet at 50 feet per minute. As such, diffusers should not be placed any closer than 6 foot on center. If diffusers are placed closer than 6 feet from each other, the collision of airstreams could result in unpredictable air motion that could potentially disrupt airflow around the hood. A layout that would meet these requirements would look something like this, where the diffusers are installed 8 foot on center and then 2 to 3 feet away from the hoods. In our next example, we'll consider a room with only one 6-foot hood. In this case, the minimum ventilation rate requirements are met when the hood is operating at its maximum flow rate of 650 CFM. At minimum flow, that requirement is not met. This means we would need an additional exhaust airflow of 285 CFM to meet the minimum air change rate we are looking to maintain. However, we have not yet considered the thermal load. With a sensible load of 17,280 BTU per hour, a supply airflow rate of 1,067 CFM is required at a 15-degree supply temperature differential to maintain temperature in the lab. For this space, we'll consider a flush face radial diffuser. Looking at the performance tables, supplying all the air through a single diffuser would result in vertical throws that have velocities well exceeding 50 feet per minute in the occupied zone. Splitting the airflow through 2 diffusers, we're able to keep velocities in the occupied zone under 50 feet per minute. Based on the performance data, these diffusers should be placed as closely together as 4 to 5 foot on center. However, in order to maintain even temperature distribution, diffusers should be placed as needed to have a well-mixed space while adhering to the requirements for not disrupting hood operation. If we now look at a solution that decouples the sensible cooling from the primary air, like chilled beams, we could have an opportunity to greatly reduce the supply airflow rate. As mentioned previously, since most laboratories use 100% outdoor air, this would result in significant energy savings, especially if there's a large quantity of lab spaces that had similar design criteria. Min and max fume hood airflows are 215 and 650 CFM, just as in the previous example. Again, the maximum hood exhaust rate exceeds the ventilation requirements. At minimum flow through the hood, we still need additional exhaust airflow to get to our minimum ventilation rate of 500 CFM. With the 250 CFM offset, this means we'll need to supply 400 CFM when the hood is at maximum flow and 250 CFM when the hood is at minimum flow. Now we need to select chill beams to be used in the space. If we want to make sure that beam airflow isn't disrupting the hood's ability to capture and remove contaminants, we'll need to select diffusers with 1 or 2-way throw patterns. This will allow for installation with the throw pattern parallel to the face of the hood. Chill beams with a 4-way pattern could result in air streams traveling down the face of the hood, preventing proper operation, and should not be used. The most efficient chill beam models are typically the 24-inch wide 2-way throw models. A simple approach would be to take the load that we have in the space, put in the maximum ventilation airflow rate, the maximum supply airflow rate, use the recommended quantity, and let the software select for itself. In this case, the result is 3 6-foot-long beams being supplied 135 CFM each at half a GPM. This would result in a reduction of outdoor air being supplied to the space by over 60% as compared to the previous example of an all-air system. If a variable volume approach was desired, selections should be performed using the same configuration and using as little airflow as possible. By increasing the total supply airflow rate to the space by only 80 CFM over the 250 CFM minimum, we were able to achieve an additional 10% reduction in the outdoor air from the constant volume approach. This is a great example of why using active chill beams in load-driven labs are especially popular due to the vast energy savings that can be achieved, which could have the potential to disrupt hood performance. I'd like to thank you for joining us today for our presentation on air distribution systems. We'll be filling some questions now. If you want to enter those into the comment box, we'll take them as they come.